Alright, so to do molecular replacement we need a similar structure. So a good way to find one is to do a blast search of the PDB. So if we go to the starting data, I see that I have my PSP28 from Thermosynechococcus elongatus FASTA file. So I will take this and do a blast search of the PDB. So this is searching for sequences that are in the PDB. Okay. Lots of people are blasting at the moment. So I paste my FASTA sequence into the blast query and I select protein data bank to search, and I search blast P and I click blast. Now I will get two hits. One is the actual structure that this is, and the second one is the correct model to use as the molecular replacement model. The PDB is a relatively small sequence database, so this should be quick. I'm going to pause. Okay, blast is taking forever, so I'll use a different search engine, HMMR, which is actually more accurate than blast anyway. So this is uses a hidden Markov model. So we will search and we will, with our sequence, and our database will be the PDB, and we'll leave the options as the defaults. I need to paste the sequence again. Blast is still going. Okay, so we see one hit, Thermosynechococcus elongatus, which is the structure that we're actually trying to solve, so we won't use that. And then the next hit is a PDB 2KVO A chain, which is the homologue from Synecha cystis, a related cyanobacterium. Okay, so let's look at 2KVO, and we have an E value of 10 to the minus 41, which is pretty significant. Do we see a sequence alignment? Show alignments. Okay, so the elongata sequence is identical, and this sequence is 60% identical, so it should be a good molecular replacement model. So let's look at the PDB. Let's make a directory for models, molecular replacement models. Okay, so let's copy the original sequence. Okay, so our structure, looking at it, has multiple superimposed structures, so will be an NMR structure. Solution structure of PS2 reaction center protein. So let's download that PDB 2KVO and save it, and we will download the FASTA sequence as well and save that. There are many ways of doing molecular replacement, some very automated. I want to do a fairly manual one so you can see the individual steps. So if we look at our FastA file from the PDB, it's the Synechococcus sequence, and then it has these H's on the end, which is the his tag. So what we will do is make an alignment of this with our structure and then mutate the PDB to match our structure and use that as a model. So that's our sequence. So if we put that together with the 2KVO sequence, we have PSB28 elongatus 2KVO. And we can open them in Clustal. Alignment. So we will need this align file. Okay, so looking at this, they look related to one another. So if we look at that alignment file, that looks about right. So we can use that. Now let's look at the PDB file. So this is the Pymol version that comes with Ubuntu Linux. Okay, let's hide the cartoon and show the ribbon. Now this is an NMR structure, so really there are about 10 models in this, so we can get those in Pymol with split states. 2KVO. Alright, so we'll get rid of the original, and I see it has 20 models. So this is a difference in philosophy between NMR and crystallography and EM. In crystallography, you make one model that matches your data the best. In NMR, you make a set of models, each of which are equally consistent with the restraints data that you have. So we see that the core of the molecule is fairly tightly restrained, and then there's a region here which is fairly flexible, and this region here, which, clicking at it, is the C terminus, HIS 120, is spread out all over. So it's not either it really is spread out like this, or its position is not determined by the NMR. It probably really is all spread out like this. For molecular replacement, this kind of thing should be removed because it will almost certainly be in the wrong place, and so will cause clashes in the molecular replacement, which will mean that the solution will be rejected. Traditionally, when doing molecular replacement with NMR, you make an ensemble model from all 20, but we'll just see if we can get away with using only one of these 20 models. So if we just look at one of them, hang on, let's look at all of them again, and just look at where the last good bit is at the C terminus. There, that's 104, and then after that is no good. Also, this bit's quite variable too, but we'll leave that. Okay, so we'll take model 1 and we'll select our model. So select 2KVO model 1, comma 2KVO 1. Okay, and then we'll select a truncated model. Model 1 truncated, comma 2KVO 001, and residue 1 to 104. Residue number 1 to 104. So if we look at that, we'll hide everything and show the ribbon. Why is that not being shown? Ah, I've defined my selection with 0 atoms. Something's not right there. Ah, res I. I was right the first time. Okay, so we see that it selected this chain except for the tail. So we can save that as a molecule. Truncated. Saved. Ah, there's another thing I forgot, which is in NMR you tend to get hydrogen atoms as well, whereas in crystal models you remove. So this is our model that we've just created. If we hide everything and show lines, we see that it's full of hydrogen atoms. So at the stage where we are now, we don't need them. If we do need them, we can add them back later. So I need to remove the H atoms. So let's do select 2kVO model 1 truncated, no H, with 2kVO model 1 truncated, and element not H. Not LMH. There we go. So if we look at the selection, it's excluding the hydrogens. Let's just double check. So let's hide everything and then just show the selection. And we seem to have omitted all the hydrogens, so that's great. So let's save that molecule. No H. No H. Let's just double check. Okay, so there don't seem to be any H atoms in there. So now I have a single PDB that is homologous to my structure with hydrogens and variable regions removed. Now I want to make another truncation of side chains that don't match. And to use that, I'm going to make use of a CCP4 program called Chainsaw. So I'm going to make a CCP4 project to make my models. So I will set it up in this directory. This is the old CCP4 interface. There is a new one which is better. So let's change project, add project, add project, and we're going to use that directory, and I'll put the date in the project name 2020-5-3 PSB28 model. And then we're going to work on that project today. Okay, model preparation. Molecular replacement, model generation, create search model, using Chainsaw, prune, so if the residues are different it prunes them to the gamma atom, so that will be the equivalent of the O atom of serine. So this is a non-physiological PDB file, but it's supposed to have atoms in the right place. Okay, so our original model is that, the truncated with no hydrogens. The alignment file from Clustal. And then that generates our Chainsaw 1 model, which has the gamma atom, so I might just call it gamma 1. Create gamma truncated PDB from 2kV. it helps to give jobs titles so you can work out what you did later. Okay, so that should run pretty much instantly, and it did. Let's take a look at it in Michoux. Okay, so that's the model. If we look at the validation, the rotamer analysis, purple means an incomplete residue. So if we look, a lot of these residues are incomplete because they have been truncated. So let's click on one. This is a methionine. Met 56. So if we look at it, we have the C beta, the C gamma, and then none of the rest of the methionine. Alright, so that is our model. The next step is to do molecular replacement of that model against the data.